Welcome students. Today in this session I am going to discuss on the topic collision properties. Before going to the topic, you should familiarize what is collision. Collision means two objects coming into contact with each other for a very short period. In other words, collision is a reciprocative interaction between two masses for a very short interval wherein the momentum and energy of the colliding masses changes. While playing caroms, you might have noticed the effect of a striker on coins when they both collide. To understand the collision very simply, consider two particles with masses m1 and m2. Let v1I is the speed of the particle m1 where the subscript I implies initial. The particle with mass m2 is at rest. In this case, the object with mass m1 collides with the stationary object of mass m2. As a result of this collision, the masses m1 and m2 move in different directions. Does it mean that all collisions should be the same? No, all collisions are not same. The law of conservation of energy holds true in the collisions of two masses, but there may be some collisions in which kinetic energy is not conserved. Depending on the energy conservation, collisions may be of two types. They are elastic collision and inelastic collision. In the elastic collision, total momentum, total energy and the total kinetic energy are conserved. However, the total mechanical energy is not converted into any other energy form as the forces involved in the short interaction are conserved in nature. Consider the same graph above, two masses m1 and m2. Here both are moving with the speed u1 and u2. The speed after the collision of these masses is v1 and v2. Then the law of conservation of momentum will give m1 u1 plus m2 u2 equal to m1 v1 plus m2 v2. From this equation, it is clear that momentum before collision will be equal to momentum after collision. Hence, here the law of conservation of momentum will obeyed. Then you consider the conservation of kinetic energy. Before and after collision, kinetic energy will identical and it is given as half m1 u1 square plus half m2 u2 square equal to half m1 v1 square plus half m2 v2 square. Coming back to the second type of collision, that is inelastic collision. In the inelastic collision, the objects stick to each other or they move in the same direction. That means after collision, both the masses will possess same velocity v. Hence, the total kinetic energy in this form of collision is not conserved, but the total momentum and energy are conserved. During this kind of collision, the energy is transformed into other energy forms like heat and light. Since during the phenomenon, the two masses follow the law of conservation of momentum and move in the same direction with the same speed v, we have m1 u1 plus m2 u2 equal to m1 plus m2 into v. From the above equation, the v will equal to m1 u1 plus m2 u2 all divided by m1 plus m2. This is about conservation of momentum. For explaining the conservation of kinetic energy, the kinetic energy of the masses before the collision is half m1 u1 square plus half m2 u2 square, while the kinetic energy after the collision will be equal to half of m1 plus m2 all divided by v. But according to the law of conservation of energy, half m1 u1 square plus half m2 u2 square equal to half of m1 plus m2 divided by v plus q. Here q is the change in energy that results in the production of heat or sound. So far, what we have discussed is collision and its different types. Coming back to our topic, that is collision properties. When we talk about molecular collision, you may think that how far a collision would be, right? The first question in your mind. If you have collisions of two molecules, how far they are, how fast they are, and how long? Especially when we talk about molecular collision, these many questions in your mind. These things are explained on different parameters, and these parameters together known as collision properties. So, in this session, I am going to discuss collision properties such as collision diameter, collision cross section, collision number, collision frequency, and mean free path. So, first we discuss about the collision diameter. According to kinetic theory, gaseous molecule treated as hard spheres. When two such molecules approach each other, a point is reached at which the mutual repulsion between the molecules become stronger. For example, you can take any similar kind of molecules, molecule A and molecule B. These two molecules, they approach each other at a point where reaches very closest. At this point, the distance between the centers of two gas molecules is known as collision diameter. It can be defined as the distance between the centers of two gas molecules at the point of closest approach to each other. It is represented by the symbol sigma. Whenever the centers of two molecules come within a distance sigma of each other, a collision occurs. Consider the collision between two identical molecules. Here, the collision diameters of molecules are of the order of the actual diameters of the molecules. For example, hydrogen, nitrogen, oxygen molecules, the values are 2.74 angstrom, 3.75 angstrom and 3.61 angstrom respectively. Suppose if the two colliding molecules are not identical, the collision diameter sigma will be equal to the average of the diameters of the two molecules. The second parameter is that collision cross section, and it was represented by sigma Cs. We know that for a collision to occur, two molecules must come within a certain distance range of sigma of each other, where sigma is the collision diameter. And also this sigma is the diameter of the circle, and thereby area of the circle will be pi sigma square. Then what is the collision cross section? Collision cross section is defined as the target area that one molecule presents to another molecule for a collision. The target area is shown in the figure. From this figure, you can realize that the radius of target area is sigma and the magnitude of target area is pi sigma square, and this will be the collision cross section. For example, consider the following reaction. that is the formation of hydrogen molecule from two hydrogen atoms, that is H plus H gives H2. Suppose the radius of hydrogen atom is 5.3 into 10 raised to minus 11 meter. We can find out the collision cross section for this reaction by taking sigma as the twice of the radius given and substitute this value in pi sigma square. Then the collision cross section will be equal to pi into 2 into 5.3 into 10 raised to minus 11 whole square, which will be equal to 3.53 into 10 raised to minus 20 meter square. The next parameter that we are going to discuss is that collision number, which is represented by Z. The average number of collisions suffered by a single molecule per unit time per unit volume of a gas is called collision number. From kinetic theory considerations, the collision number for a given gas is given by Z equal to root 2 pi V sigma square rho, where V is the average velocity, sigma is the collision diameter, and rho is the number density. Number density rho is the number of gas molecules per unit volume, and it is given as rho is equal to N by V. From the above expression of collision number, we can find out its unit by substituting the unit of each terms. So the unit of Z equal to meter per second into meter square into meter raised to minus 3, which will be equal to second inverse. Now we are going to talk about the fourth property of collision, that is collision frequency. It was represented by Z11. Collision frequency is usually defined as the total number of collisions between the molecules of a gas per unit time per unit volume. Simply, it is the product of collision number and total number of molecules. That means collision frequency Z11 equal to collision number into total number of molecules. Since rho represents the number density, we can substitute the total number of molecules as number density. Then the equation for collision frequency changes to Z11 equal to collision number into rho, which is equal to root 2 pi V sigma square rho square. Let's consider the collision of one type of molecules. Then the collision frequency is given as 1/2 of the above equation. Then Z11 equal to 1 by 2 into root 2 pi V sigma square rho square, which will be equal to 1 by root 2 pi V sigma square rho square. And the unit of Z11 is second inverse meter raised to minus 3. This equation implies that the collision frequency depends on average velocity V, collision diameter sigma, and the number density rho. Obviously, for a given rho and sigma, the collision frequency is directly proportional to the average velocity V. We know that the average velocity is root of 8 RT by pi m, and substitute this value in collision frequency, then Z11 equal to 2 sigma square rho square root of pi RT by m. At ordinary temperatures and pressures, the number of bimolecular collisions in a gas is of the order 10 raised to 34 meter raised to minus 3 second inverse. Now we will discuss the effect of temperature, pressure, collision diameter, and number density. From the above expression, it can be seen that at a given pressure, collision frequency is directly proportional to square root of Kelvin temperature. It is also obvious from the expression for Z11 that at a given temperature, collision frequency is directly proportional to square of number density. But we know that the number density rho is equal to n by v. Thus, the collision frequency is directly proportional to square of the number density and also the square of the pressure of the gas and inversely proportional to volume. Then consider the effect of collision diameter. At a given temperature and pressure, collision frequency is directly proportional to square of the collision diameter of the gas. So, it can be summarized as collision frequency is directly proportional to square root of temperature, square of number density, square of pressure of the gas, square of collision diameter and inversely proportional to the volume of the gas. Suppose when consider the collisions between two different types of molecules, then the number of collisions between molecules of type 1 with molecules of type 2 per unit time per unit volume is given by Z12 equal to 1 by root 2 pi v square sigma square rho 1 square into rho 2 square, where rho 1 and rho 2 are the number densities of type 1 and type 2 molecules. Our last property is mean free path and it is represented by lambda. The distance travelled by a molecule between two successive collisions is called its free path. Since collisions occur randomly in a gas and the speed of the gas molecules may change with each collision, the free path changes from time to time. So, a term called mean free path is commonly considered, and mean free path is average distance travelled by a molecule between two successive collisions. If L1, L2, L3 and L4 are the free path for a molecule of a gas, then its mean free path will be equal to L1 plus L2 plus L3 plus etc. up to Ln all divided by n, where n is the number of molecules with which the molecule collide. Mean free path is also equal to the ratio of average velocity and collision number, that is lambda equal to v by z. Then substitute the value of z, then the equation changes to v divided by root 2 pi v sigma square rho. Cancel like terms, then mean free path equal to 1 by root 2 pi sigma square rho. So, lambda is inversely proportional to sigma at constant temperature and pressure. That is, larger the size of the molecule, then smaller will be the mean free path. Then how this mean free path depends on temperature and pressure? To understand this effect, substitute number density as P by kT in mean free path equation. Then the mean free path equation changes to kT divided by root 2 pi sigma square P. From the above equation, the mean free path of a gas is directly proportional to the Kelvin temperature, that is greater the temperature, greater the mean free path. Also, the mean free path of a gas is inversely proportional to the pressure. That means the greater the pressure, the smaller the mean free path. Besides the temperature and pressure, mean free path also depends on coefficient of viscosity eta. Coefficient of viscosity related to mean free path by the equation eta equal to 1 by 3 V d lambda. Here v is the average velocity, and this average velocity will be equal to root of 8 RT by pi m. D is the density of the gas, and D equal to m rho divided by n0, and mean free path lambda equal to 1 by root 2 pi sigma square rho. Substitute these three equations in coefficient of viscosity equation, and which changes to eta equal to 2 divided by 3 pi n0 sigma square root of mRT by pi. The above equation reveals that eta increases with increase in temperature. That means eta is directly proportional to root of T. Reason is that at higher temperature, the momentum is transported more rapidly through a given area, and hence force has to be increased to maintain the motion of the layers of gas. While for liquids, molecular attraction is dominant. Therefore, if the temperature of the liquid is increased, its cohesion and hence viscosity decreases. Thus, viscosity of gases increases with temperature, while for liquids viscosity decreases. But in the case of pressure, eta is independent of pressure, because with increase in pressure, more molecules are available to transport the momentum, but only a few can do so because of their reduced mean free path. Another important feature is that we can calculate eta for a given gas at a specific temperature. That means viscosity measurements can be used to calculate the molecular diameters of gases and the mean free path. We will learn more about the coefficient of viscosity in the next session. So, with this, I am concluding the session. Thus, today we have discussed different properties of molecular collision, such as collision diameter, collision cross section, collision number, collision frequency, and mean free path. Also discuss the different factors that depends on these collision properties. Hope the discussion is clear to you. Thank you.